Okay, question 8 is definitely nasty and sneaky. If you get it, great. If you don't get it, don't worry. Don't run off and become a history student or something like that. It's very, very tough, and I really don't expect many people, if any, to get it, but it's always worth throwing out those challenges. So anyway, here's the molecule that we're looking at. Okay, we're taking ethene and we're sticking a chloro on it, so chloro or chloroethene. And what we see is we've got 1, 2, 3 hydrogens, okay? And we've got 1, 2, 3 peaks. So remembering, of course, that chlorine is very nice and electronegative, we would say that the hydrogen that's on the carbon that's attached to the electronegative chlorine would be that one there, and then the other 2 hydrogens would be there. Now, why, you say, are these not the same? They're bonded to the same carbon, blah, blah, blah. We've always said that hydrogens bonded to the same carbon are going to be equivalent. Well, remember, there is no rotation around the carbon-carbon double bond. So therefore, this blue one will always be on the same side as the red one, and the pink one will always be on the same side as the chlorine. And so by virtue of that, the pink and the blue ones are going to be different hydrogens. Okay, now I'm not going to worry about assigning which one of these is blue and which one of these is pink, because we're really not into it to that great detail. What I want you to see from that is that these are not the same hydrogens because of the non-rotation around the carbon-carbon double bond. You're always going to have the pink one next to the chlorine and the H1, the blue one, next to the red one. Now we can see that even more amusingly when we go to the high-res spectrum, because now this one little peak here splits into 4 peaks, all of equal height. And of course, ordinarily we'd say, well, hang on a minute, this is next to a carbon that's got 2 hydrogens on it, 2 plus 1 is 3, so why wouldn't this be a triplet? And then these 2 down here, we would say, well, hang on a second, why are these not just going to be a doublet because we're next to a high carbon with 1 hydrogen on them? Okay, well, now if I blow things up a little bit, first of all, we'll start here, and what we see is 2 doublets, because this red hydrogen, which is giving this signal, it's split by the blue one, and of course that's 1 hydrogen, so it would give us 2 peaks, and it's split in a different way by the pink one. So there we are, we've got another 2 peaks. So 1, 2, 3, 4 peaks here, because it's being split by 2 different adjacent hydrogens. Okay? Blow this one up more closely, and what we see is that it's not 4 peaks, it's actually 2, 4, 6, 8 peaks. Where on earth does that one come from? Well, imagine that you are this blue one, okay? You are now going to see 2 different hydrogens there. You're going to see a pink hydrogen and you're going to see a red hydrogen. And so your signal is going to be split, first of all, into a doublet by virtue of closeness to that pink one. And that's probably one of these nice close ones here, okay? But then each of those is going to be split further because of this red one. So you get what's called a doublet of doublets, okay? A doublet due to the pink one, and then split again into a doublet with the red one. So we see a doublet of doublets for each of the blue and the pink ones. I'm not going to say which one comes from the blue, which one comes from the pink. What's important is that you realize that even though we've only got 3 hydrogens in this molecule, we get 3 distinct signals and then massive doublet of doublet splittings because all of those hydrogens are different. Like I said, a tough one. Hopefully some of you got it. Those who didn't, please do not stress.